Hi guys. So I do want to really apologize with you guys for not being able to catch up with the videos. I've been studying for my exam and I'm also taking art class currently, so some of the projects are taking a little bit longer than they should, but on exam wise I'm working on them, but good thing that I take them during this week so then I can be finally done with them and then I can catch up with you guys in the videos. So I know that Alexi, he's doing SN1 and E1 first, but when I did my slides, the book, it has SN2, E2, and then SN1 and E1. Of course, I'm gonna make a video on SN1 and E1, but I do have E2 reactions programmed to be my next reaction that I'm gonna look into. So I'm gonna look into E2 now, and then possibly like for tomorrow or in a couple of days. I take my exam on Wednesdays, so I'll be maximum by Wednesday I will have a video out for SN1 and E1. So you should be pretty good and catch up with at least with where the class is at. So today we're gonna do E2 reactions. So then alkyl halides, they can undergo elimination reactions. These reactions involve the use of bases than nucleophiles. So technically, a nucleophile can be, like for example, a nucleophile, we know it as OHH, for example, or H2O. So then this one could be technically a nucleophile because we know that nucleophiles, they need like things like electron pairs, or maybe we need maybe like a double bond. We need something that's like electron source, and maybe a carbon negative, like a double bond oxygen, you know. This one goes negative, so this one becomes our nucleophile, and this one becomes our electrophile because it's positive. So then that one could be technically like a nucleophile, but it can also work as a base. So then basically E2 reactions are for bases, while SN2 or substitution reactions in general, they're for nucleophiles. So E2 reactions, when treated with a strong base, an alkyl halide undergoes a type of elimination process called beta elimination, known as 1,2 elimination, in which a proton is removed from the beta position. Last class we learned what's alpha and beta positions, and then the halide is being ejected as the leaving group X. Alkyl halides are normally represented as X, or like the halide, the chlorine, the bromine, the iodine, from the alpha position, and a double bond being formed between the alpha and the beta positions. So you can see here, let's see if I erase my notes, this will be kind of like the how the arrow system will work. So like it says, we go through beta elimination, or as 1,2 elimination. So the thing is that you have your alpha and then your beta. So then your base is gonna take a hydrogen from your beta carbon. Your alpha carbon is normally the one that's gonna carry that alkyl halide, or that halide, which is chlorine, bromine, or iodine. Therefore, your beta positions are technically gonna be this one down here, or for example this one down here, or even this one down here can be your beta positions. So beta positions are the ones that are next to the alpha ones. So then your base normally is gonna take a hydrogen from your beta position. So then you can see we're taking that hydrogen, and therefore by doing that, we're breaking this bond and we're putting those electrons on that carbon. Therefore, we're gonna end up with something like this. And also, we have to take into account that at the same time, our halide is gonna leave. So then this one will be carbon positive. In here I have a carbon, carbon. Or I can just count it like that, I guess. Carbon, 1, 2. Since we already know that there's carbons in there, so we don't make it too complicated. Okay, so then we have our focus carbons in there. And then technically you can see where that double bond came from, right? Because if we're left with something like this, we can totally make a double bond in between those two. And then we can end up with something like that. And you can see that our base took that hydrogen, because in here we ended up with hydrogen base. And then we can see that our halide left, because in here our halide left, and then it was left with a complete octet. So E2 reactions. So as SN2 reactions, they act in a concerted mechanism. Therefore, everything happens at once. So we have a loss of a leaving group and a proton transfer at the same time. While for things like E1 or SN1, we have a stepwise mechanism. So consider it's for E2, SN2. While stepwise is mainly for E1, SN1. So the main difference is that with E2 we have loss of a leaving group and proton transfer, while SN2, if I'm not wrong, is about nucleophilic attacks and loss of leaving groups. Which kind of makes sense because, you know, SN2 has to do with nucleophiles. We have a nucleophilic attack and that causes a leaving group. So E2 reaction. So both mechanisms involve proton transfer and loss of leaving group. The difference is that consider both events, they happen at the same time. But stepwise, the first thing that happens is the leaving group to give an intermediate carbocation, and then a proton is transferred in a separate step. So E2 kinetics. So it will be the same rate as an SN2 reaction, just that in this case, instead of a nucleophile, we have a base. So then the rate will be rate equals K times alkyl halide times a base. And in other words, the rate of reaction is dependent on the concentrations of the alkyl halide and the base. For example, doubling the concentration of the alkyl halide causes the reaction rate to double. E2 reactions are bimolecular since the alkyl halide and the base collide with each other. And you can see the mechanism just in a gradient way. Like as we said, a base removes a proton from the beta position of the alkyl halide. So you can see this is our alpha because it carries that halide. And then we have beta positions. And then our base is gonna take hydrogen from one of those beta positions. And then this causes a loss of leaving group, and then like we saw previously, we're able to do a carbon-carbon bond because we will end up with something like this. So we're able to do a carbon-carbon bond, and we would end up with something like this. And of course, our base with a hydrogen and our halide all by itself. So let's practice. So the following reaction exhibits a second-order rate equation. What happens to the rate if the concentration of chlorocyclopentane is tripled and the concentration of sodium hydroxide is the same? So I'm always gonna repeat this. Things like sodium and that stuff, we just think like they're not there, because I mean they're there, but when we react with it, we have this type of formation. So therefore they don't really do anything on the reaction. Therefore I just call them as spectators. Well, this is what reacts on the reaction. So instead I just write it just like this. Okay, so since we're dealing with E2 reactions right now, this one technically will be our base. And then my alkyl halide. Alkyl halide is something it's a chain that's carrying a halide, just like a bromine, a chlorine, an iodine. So then this one will be my alkyl halide. Also, that chlorine says it all. That will be my halide. So as we said, it's gonna be the same as an SN2. We're gonna have our rate equals K times alkyl halide, but this time it's gonna be multiplied by a base instead of a nucleophile. So we have K, and it says the concentration of chlorocyclopentane. So this is chlorocyclopentane is triple. So this one is times 3. So this one's gonna be tripled. And the concentration of sodium hydroxide will be this, and it's the same, so it means that it's kept, we can just put it as 1, just because it's got the same, you know, we're multiplying, so it will be 1. And then 3 times 1, it will be 3. K, I just put it as K. I just know that our rate is gonna triple, and that will be our answer, just because the concentration of our alkyl halide tripled and the concentration of our base stayed the same, our rate ended up being tripled. So you can try it on your own now. So it's technically like the same problem. Like we said, this one's a spectator. We don't think about it that much. We're doing E2. So then technically we're just gonna be doing this one is gonna be our base, and this one's gonna be our alkyl halide because it's carrying that halide. So if we're looking towards the future, this one can be an E2 SN2. Therefore we can have products for E2 and SN2. The products of E2, they're preferred just because we're doing a secondary. This will give rise to, this is a secondary like alkyl. And then the thing about SN2 is that they prefer metals over they prefer metal, then primary, then secondary, then tertiary. So therefore SN2 wouldn't be as fast as E2. That's why E2 products will be preferred in this case. You'll be like, then why can't we do E2 and SN2? Because the thing is that SN2 can happen on primary metal, primary and secondary halides. It doesn't happen on tertiary, but this one is a secondary, so we can have SN2 products. But that's just looking for the future. So this is one of our products, that's correct, but we do have way more products. So then, but right now we're just doing second rate equations. We're just looking how our rate is affected, so don't get stressed. So then, as we said, our rate is gonna equal K times the alkyl halide times the base. Okay, so then alkyl halide, if the concentration of the chlorocyclopentane remains the same, so we're just multiplying by 1, and then the concentration of sodium hydroxide is double, 2 times 1, 2, then k, that means that the rate is double. See, so then just finding out the rate is not that hard. It's pretty simple. You just have to memorize those equations. That if you do a little bit of practice, I think it's not gonna be really hard to remember that. Okay, so now we're doing the effects of the substrate structure on the rate of E2 reactions. So notice tertiary substrates can undergo E2 but not SN2 reactions. So this goes way back to what I said on the previous slide. SN2 reactions can only happen on primary and secondary. So there's no tertiary for SN2. While E2, it can happen on primary, secondary, and tertiary. So what's the reason? It's because of steric hindrance, or as I like to call it, bulky. It prevents the reagent from acting as a nucleophile. Like you can see, hydroxide functions as a nucleophile, but the thing is that this is too bulky. So SN2, which includes a nucleophilic attack, it can't technically happen. Well, elimination, hydroxide functions as a base, but it's able to, because remember that elimination, it has to do with that alpha and then that beta, right? So we have our carbon. So then it's not really attacking anything. It's mainly just taking a hydrogen away from it. Therefore, it's like it wouldn't be like it wouldn't cost too much energy, or wouldn't be like too unstable. That's why elimination is possible on tertiaries. And SN2 is not really able to do tertiary reactions because of this. It's too bulky. Okay, so just as a little break, stability of alkenes, double bond. So then the main idea, cis alkenes are less stable than trans alkenes. And that's what we learned from previous chapters, because with cis, it produces it has way more interactions, because they're able to touch each other, while on trans, they're not really able to touch each other. And how do you identify whether cis or trans? It's mainly by priority groups. So then, for example, in here, we know that we have hidden hydrogens. This one, of course, this one is our main priority group on the left side, because carbon is more, it has a higher priority than hydrogen. And on the right side, carbon has way more priority than a hydrogen. Well, in here, we do have still hidden hydrogens. So if we compare, we already know carbon has more priority, carbon has more priority. But the thing is that these two, they're able to have interactions together, causing it to have a little bit more energy than when it's trans. So then we will prefer a trans over a cis, just due to energy. So stability of alkenes, there are steric effects. So the more substituted, the greater the stability. The more substituted, it just means the more carbon-carbon chains it has in here. So for example, a monosubstituted, so we just have one carbon-carbon. In here we have 1 and 2 carbon-carbons. Here we have 1, 2, and 3 carbon-carbons. And then in here we have 4. So the more the better. So then right now we're just gonna practice to identifying monosubstituted, disubstituted, trisubstituted, and tetrasubstituted, and just technically seeing which one will be more stable. So then let's see. So then just by looking at this, I can already see that this one is gonna be disubstituted. Just by looking at this, I can see that this one's gonna be tri-substituted. And then let's see. And just by seeing this one, I can see that this one is gonna be mono-substituted. And from the previous slide, we said that we like tetra, then tri, then di, and then mono substituted. So then let's see, we said that this one was gonna be di substituted. This one is a tri substituted. And this one is a mono sub. So let's see, so then 1 is gonna be the most stable, and then 2, no, and then 3 is gonna be the least. So then my most substitute is gonna be my most stable, so therefore it's gonna be this one. And then I have my di, which is my in between, and then I have my mono substituted, which is my least substituted. And then let's use the same thinking. 1 is the most stable, and then 3 is the least. So then I'm just gonna put in here, 1 is the most stable, and 3 is the least stable. Okay, so now you can take a second to look at it. Okay, so we're just gonna identify in here. This one's pretty nice. We have a tetra. In here we have a 1, 2. We have a di sub, tetra sub. And then in here we have 1, 2, and 3. We have a tri sub. So we can see that the tetra substituted is gonna be the most stable. The second one, the in between, is gonna be the tri, and then the least stable is gonna be the di substituted. So stability of cycloalkenes. So this is mainly like things that you need to know, kind of like slide. So then cycloalkenes with less than 7 carbon atoms cannot accommodate a trans pi double bond. But an 8-member end ring is the smallest ring that can accommodate a trans. So then for you to be able to have a trans double bond, to be stable at a room temperature, it needs to be like an 8-member, or it needs to have 8 carbons in total. This one will be like the most stable if you were to make a trans one. But also you have to take into account that cis is cis, but at least for trans, for it to be able to be stable at room temperature, it needs to have 8 carbons. Well, if it's this configuration, you can do like cyclopropene, cyclobutene, cyclopentene, cyclohexane. You just have to take into account that these ones are cis, while the other one is trans. So reduced selectivity of E2 reactions. So elimination reactions can produce more than one possible product. You can technically notice because you can see that we have different beta positions, right? Like we know from previous chapter, we know that we only have one alpha position, but we can have up to 3 different beta positions. And they can actually give rise to different products. So for example, let's see. I just wanted to add my hydrogens on my beta positions. So then you can look at this too. So then you can see that I can have a total of 2 different products in this one. And that is because my alpha from my left doesn't look the same as my right. Or like my beta position that doesn't look the same as my left and my right side. That's why I have too different. Or I mean, if it's more easily visually, I can totally just do this for you guys. Let's see. Yeah, I can write in here. Okay. So then we know my alpha, beta, and beta. So then why don't we put this one? Because these two, they're the same. This is a CH3, this is a CH3. That one, it is a beta position, but it will give rise to the same molecule. That's why they're not really considering that one. Okay, so once we know that, we can do this. So I have option 1 and option 2. See, alpha, beta, beta. Oops. Okay, so then let's look at option 1 at least for now. Okay, so I'm gonna remove a hydrogen from here. And I've been given, according to this, I've been given this space. So then I did notice that I did mention that this beta position has actually 2 hydrogen. So then since we saw the arrow system for elimination reactions, we can take a hydrogen from that beta position. And remember, we're doing E2, so everything happens simultaneously. So there's not really like carbocation rearrangements or anything just yet. So then we have this, our alpha. This one leaves, so our alpha is gonna carry a positive charge. While this one's gonna carry that negative. Remember that this one is just like a hydrogen that's in there, so then I can technically act like it's not there, but then I can eliminate it when I draw my final product. So then I have this. Remember, we're gonna do like a double bond between that positive and negative charge, so we're gonna do a double bond in here. That's how I was able to get one of the products, like you can see in here. And also remember, I just took out that hydrogen, like it's there, but I just didn't show it. Because it's here. But just for you to be able to see that product, then to look like it exactly. So then I said that I have 2 options. So I have option 1. So then let me do my option 2. And we're gonna use that same base. So then this beta, it has 3 hydrogens. Okay, let's see. Alpha. They have hydrogen, double bond negative. Okay, and let me erase this one. Because also, remember, we're doing E2. That means that one left to have a positive charge. So then, positive and negative, we're gonna do a double bond in between those 2. We have hydrogen, but if we don't show it, it's gonna actually end up looking just like this. And it looks just like our product, right? So then you can see that I was able to do 2 different products, or I was able to get 2 different products just using that same base. And as we saw before, This is an example of radiochemistry. Both products can be formed, but the more substituted alkene is generally observed to be the major products. So in this case, the major product is going to be the trisubstituted over the disubstituted. As we saw, trisubstituted, they're more stable than disubstituted. So that's why that one will be the major product. But we have things called side-step and Hofmann products. So then side-step is called the more substituted alkene. So side-step can be a minor product if the substrate and the base are really bulky. And then Hofmann is the less substituted alkene. So then the thing is that we have in here, we have our base, okay? And we have two products from here. We have a trisubstituted and then we have a disubstituted. So then when our base is not really that bulky, then our major product is going to be the more substituted. And our minor product is going to be the less substituted. But when our base is really bulky, then the more substituted is going to be our minor, while the less substituted is going to be our major. So the bulkier the base is, then that means that our less substituted alkene or less substituted product is going to be our major products. So you have to take that into account. So like in this case, for example, this base is not bulky. This one's not bulky at all. Like if you were to draw this one, you could technically be able to see that this one's not bulky. This is an ethyl, so then it's a 2-carbon methyl and ethyl, and you would see that one's not bulky at all. So then that means that our more substituted is going to be our major product. Well, for example, if that one was like really bulky, really big, then if our base was really big, then it will be the opposite. Our major product, it will be the less substituted. So what are some examples of bulky bases? So it could be terbutaoxide, diisopropylamine, triethylamine. But these are not the only bulky bases. We have way more. These are just a few examples. So then we can do a little bit of practice. So then predict the major and minor products. Okay, so like we said before, I have this one is bulky. So then I have my alpha, which is what carries my chlorine. And then I'm gonna have my beta positions, right? So I have this one, and this one. So if just by looking at that, I can see that I'm gonna have just 2 products. Just because this one and this one, they are the same thing. So then I only have 2 products. So then I have options, so that is quite nice. So then let's see. The bad thing is that there's not that much space, sadly. So I'm gonna try my best. Okay. So then option 1. Okay, this thing is here, chlorine. Okay. So I'm gonna take out from this beta position in here. So I have a hydrogen, hydrogen, hydrogen. And then I'm reacting with turbio, okay? When it's like that, I just write okay. And then I just put it with a negative. But I just take in mind that that one's gonna be like really bulky. So then remember in how E2, our base just takes a hydrogen from that beta position. Okay, so then let's see. And then we have to remember that we are gonna have a living group as well, so we have a positive in there. And then we have this one goes here. Then I have a hydrogen here, negative. And I am able to make a double bond with those two. So then I have one of my products. It would actually end up looking like this. So then we have this one will be disop. I just want to take that one into account for now. Okay, and I said I have two options, so let's do option 2. So I'm gonna take from this beta position now. I only have 2 hydrogens. It doesn't really matter which one I take for now because we don't have any stereochemistry or anything. So then we have a leaving group. We are also gonna take a hydrogen from it, from our beta position. We have a positive. And then we have a hydrogen, we have a negative. And then we can do a double bond with that one. Okay, so then let's see, let me check. Oops, the thing is that I don't want the products to mesh together or anything, but I do want to show you how the product's gonna look like without that hydrogen, so we can tell whether it's mono, di, or tri, or tetra substituted. Okay, so then this one is gonna be tri. Okay, so then the thing is that we have to identify which one's gonna be our major and our minor products now. So then, since this one's really bulky, our major product is gonna be the less substituted. That means that this one's gonna be our major. This one down here. While this one, since it's the most, is gonna be our minor. So we do have to take that base into account. Okay, so the next one. So we can identify our alpha position. We have our alpha in here, and then we have a total of 3 betas, but 2 of them, they look the same, therefore we're just gonna end up with 2 products. So then we can either take from here and from here to get those 2 products. So then we again have option 1. We can draw this, and this. I think I would prefer I would prefer to take it from here. This one would leave. Okay, so then I have OH negative. Remember that Na is just gonna be a spectator. So then my base is gonna attack this, or it's gonna take a proton from it. It's gonna do a proton transfer. We're gonna be breaking that bond. Like we mentioned, our halite's gonna leave. This one would end up being positive. This one would end up being negative. And then we're gonna make a double bond with that. Then we would end up with something like this. And then this one is disop. Remember, we still have hydrogens, just I'm not really showing them, but they're there. Okay, so then I can draw my option 2 now. This one, this one, this one, this one. We have a living group. We have a positive in here. We have a negative in here. We're gonna have a double bond right there. And remember, again, we do have a hydrogen in there, but I'm just not gonna show it. And then this one's gonna be dry sub. So then remember, so since this one's not really bulky, that means the more substituted is gonna be our major product. Therefore, the more is the dry, so then this one's gonna be our major. Well, this one's gonna be our minor. Yeah, so this ones, they do take quite a while, so, but I think if you get like the main idea of it, I think after some practice it is pretty easy to do them, or it's very doable, I would say. Okay, so now you can look at your next problem down there. Okay, so then I can solve it with you guys. So as we said, this one is just gonna act as an spectator, Na plus. We have ON. So since we said before that one's not really bulky, so then not bulky, we know that the major product is gonna be the more substituted. That's quite nice. So then if we analyze, let's see, we have alpha, beta, beta, beta. Alpha, we have 1, 2, and 3. So then the thing is that you can see we have 3 beta positions, so you'll be like, ooh, we can do 3 products then, but not really. So we can do 1 and 2. We could do 3 if we wanted to, but the thing is that this beta position doesn't have any hydrogens, so then therefore we only have 2 beta positions. So then we have option 1 and option 2. Okay, so then let's see. Okay, so then my let's see. This one chlorine, this one in here. Let me draw it for this one in here as well. I know it doesn't look that good, but I tried my best drawing it. Okay, so then I'm gonna concentrate on this one on top. That one has 1, 2, 3. Yeah, 3 hydrogens, okay. And then my base is NaON. Okay, so what happens? We have a proton transfer and then a leaving group. And they both happen at the same time. So this one we're gonna have a plus, have hydrogen, hydrogen, negative, and then we do a double bond with that one. And then we end up with something like this. since they're hydrogens, we can act like they're not there. So then we'll have a disub. So then for the next one, we already did this one, so we're gonna do this one in here. This one has 2 hydrogens. We're gonna do a proton transfer, and then this one leaves. So this one has a plus. And then in here we have this hydrogen negative. We can do a double bond in here. And then we're gonna have a trisub. So let's see which one's gonna, since it's not bulky or major product, it's gonna be the more substituted. And then our minor product is gonna be the less substituted. Okay, perfectly. Hopefully you got that one right. And then we can look at this one. So you're gonna find quite nice that this one's a lot more easier because all of the beta positions, they look the same, therefore we only have one product and it's our only product. So we have 1 alpha and we have 3 beta, we said, but if you look at it, they're all the same. So then we only really need to take 1 hydrogen from one of the beta positions. So then we mentioned that, or how's it called, or terbutyl, we can write just as okay. It's just gonna be a negative. This one's bulky. And it's gonna take a hydrogen from that beta position. We have 1 hydrogen. This one's negative. Our bromine left. So that one's positive. And then we can do a double bond in between. And technically it's not really gonna look like that. But as long as you're able to show the right amount of carbon-carbon bonds in there, then that should be pretty good. But if you do want it to look way nicer, you can also make it look like this. But as you can see, we have the right amount of bonds, of carbon-carbon bonds. And since that one is our only product, we don't technically have minor or major. And also it's a tertiary, so we don't technically have even SN2 reactions to be able to be made with this one. So stereoselectivity of E2 reactions. So this is when it gets a little bit harder. So no, stereoselectivity of E2 reactions. So then in an E2 reaction, there is a stereochemistry. So then we're able to actually get a major and then a minor product. The major is going to be the trans because it has less energy, more stable. No, it has less energy, makes it more stable. While this one says it creates more energy and it is less stable. So trans products being the major products, cis products being the minor product. This due to stability, the trans alkene is more stable, less energy than cis alkene. So stereospecificity of E2 reactions. So then in the previous reaction, our beta position had 2 different protons with the trans conformation being favored. So then you can see that in here we have our beta positions, they look the same, right? So we'll be given the same products. But the thing is that if we consider like the stereoselectivity, or if we consider that we're gonna have hydrogens in a wedge and dashes, then you can technically see that if we take out the hydrogen in a wedge, we're gonna have it either being cis or trans. But if we take one in a dash, then it's gonna be complete opposite if we were to take one from the wedge. So if we have this type of relationship, then we will technically be able to get cis and trans. We will be able to get both products, but the one being favored, it will be the one in the trans position. But if we consider a case in which a beta position contains only one product, so for example, if I was to have a CH, and then instead I will have this on a chlorine, for example, that means that there will be no cis and trans mixture, and we'll have to find out which one we can obtain. So then, for example, in here we have NaOH. We have our alpha, our beta. Technically, this one doesn't count because, it doesn't have any hydrogens. Okay, so then we have our leaving group, and we have our beta position. This one's removed, it's taken out. So then you can see we have a phenyl and a hydrogen pointing on the same way. Well, we have our metal, this weird thing, just pointing on the same way. So you can see we're technically having the same relationship that, for example, if they're on dashes, they're going to be on the same side. Well, if they're on the wedge, they're going to be on the same side. And it technically doesn't matter where it's up or down, but I normally just put all my wedges up, and then I put my dashes down, because it's the same thing we've been doing, or the same way we've been thinking. So how does this work? So why only one stereoisomer and not both? In order to achieve this kind of orbital overlap, the 4 atoms must all lie in the same plane. The proton at the beta position in the leaving group will have to ultimately form the double bond. They have to be coplanar. So as you can see here, the bromine that left and the hydrogen that was taken from the base, they were out on regular bonds, so they weren't on a wedge or in a dash, so they had to be coplanar. So remember that carbon-carbon single bonds, they can be rotated. Therefore, before the reaction occurs, to achieve this coplanar arrangement. So you'll be like, so what if my hydrogen that has to leave is not on a wedge? You can just rotate it. No, like, for example, if this one was on a wedge, if this one was on a wedge and this one was just a regular bond, you can just rotate it until that one is just in a normal bond. So then you're able to have that coplanar relationship, and you're able to do that double bond, and then you can assign, your wedges and then your dashes. Technically you'll be like, oh, if we all have wedges and dashes, then wouldn't it be the same? No, because then you do priority groups, and when you do priority groups, you technically cannot predict, because you're gonna have different things connected to it, so you cannot predict whether it's gonna be cis or trans. So conformations, so anticoplanar and syncoplanar. So anticoplanar is gonna look like this, while syncoplanar is like this, so eclipse and stagger. So then when you do elimination reactions, your anticoplanar ends up technically looking like this, because you're removing two of the groups. So it ends up looking like that, and then you're able to form that double bond. So how to determine stereoisomerism of the product? So I just did the same thing in here as I did in here. You can see I put my R1 is on a wedge, so I put them on the same side. This one is on a dash, so I put them on the same side, or same side down. This one's on a wedge, R1, and R2 is on a wedge as well in this case. So as you can see, R1 is up and R2 is up. And then in here we have this one dash and this one wedge. No, this one dash as well. So then we have dash dash. So then you're technically able to see that no matter, no matter the color, no matter anything, like it's mainly about that relationship, that everything pointing up is gonna be wedge wedge, while everything pointing down is gonna be just dash dash. So it's something just to remember, and I would say it is pretty helpful. So then main ideas, it's a lot. I know it's a lot of information to take in, so just practice. So then one hydrogen in a wedge and another in a dash on the beta carbon will get cis and trans conformations of alkene or both. If we only have one hydrogen on beta carbon, then we either get cis or trans, not both. Before forming alkenes or parent, hydrogen and leaving group need to be on the same plane, regular bonds. So that goes with that coplanar thinking. No wedges and dashes. If not coplanar, don't stress, we can always rotate it until our carbon-carbons are coplanar. Wedge group face the same way and dash group face the same way. Okay, so give me a second. Okay, so let's practice. So identify the major and minor products of the E2 reactions. So then these ones, they do take a while. They do take a little bit longer, but we can try our best to do them as fast as possible. So then we have to identify our alpha and then our beta positions. Our alpha here. Then we have beta. So this one's quite nice just because you can see that in here we have hydrogen on a wedge and hydrogen on a dash. And remember what we said, when we have both on wedge and dash, or we have our beta position has hydrogens both on wedge and dashes, then that means that we're able to actually have cis and trans. So we don't technically have to exactly find out whether it's gonna be cis or trans. So then, for example, if we were to have a base, technically, I mean, we do have a base, but if we were to assign one, then we do have to put our bromine. We do have to put our bromine first on a normal bond, but then afterwards we'll get cis and trans. So then let's see. I have my carbon-carbon bonds in here. This one's my alpha, this is my beta. And then as you can see, I have my bromine. I have a hydrogen on a wedge. And then I have this weird thing on a regular bond. Then I have this one wedge, dash. And then normally things like rings, I just name them phenol. And then, you know, when you have to draw your final structure, I then afterwards draw, you know, the whole ring. Have carbons. So we said that we want them to be coplanar. I don't technically have to do this for this one, but I just want to show you guys for future sake. So for example, I can rotate this one, and I just think of it as a steering wheel technically. So then I just keep my same bonds, and I'm just gonna do like a steering wheel. So I'm just gonna move my hydrogen up. I'm just gonna move, you know, hydrogen, and then I'm just gonna bring my phenol down. Well, I can also rotate this one. And then I can bring, let's say bromine. I can bring this one up. Yeah, okay. So, and I can keep this one normally. So if I do the same thing as a steering wheel, I can bring this, the bottom one up, and then the top one down. Let's say this one goes up, hydrogen and bromine. So I would end up having a hydrogen bromine, you know, on just regular bonds. So since they're just on regular bonds, I can actually do an E2 reaction because we need them to have that coplanar relationship. So then once those two are done, I can do a double bonding here, and I can have my phenol group. That's it. We said that we're gonna want wedges up, so then I'm just gonna have hydrogen, and then I'm gonna have my phenol pointing down, and then I'm gonna have this one pointing just down. So if we do priority groups, this one will be technically my cis. And then looking down at this one, I can again just rotate it. Just rotate this carbon again. Just so I can have that other hydrogen. Let's see if, let me erase that. I would technically still keep like the right side by itself. So then I would just do the steering wheel again. Oops. And I would bring this one up. So then I would bring my phenol. Oops. I will bring my phenol here if it wants to write. Write my phenol here. I'll put my hydrogen here and put a hydrogen in there. So technically I still have a hydrogen bromine relationship. So those ones live. But then, for example, my phenol would end up being on a wedge, and my hydrogen will be on a wedge. And then I'll have a hydrogen on the dash. And then I will end up having this weird thing on a dash. So then you can see I have a trans relationship in here. So then this one will be my major product. So then that one will be my major. And this one will be my minor. because that one will be my cis. So I'm sorry if it's if it took you a little bit longer. The thing is that it's a little bit complicated to explain the steering wheel method technically. So then you can try it on your own. I know it's a little bit complicated, so if you don't feel comfortable yet, we can solve these ones together. So then this one's quite nice also. It seems like that one's also gonna be you know, we only have one alpha, and then this beta doesn't really work, so then this one works. And then apparently it's two hydrogens, so then one is gonna be in a wedge and then another one's gonna be in a dash. Okay, so then let's see, beta, and then I guess we're just gonna have to assign a base because we're technically not giving one. So then we know that when we have two hydrogens on bases, we can technically we have two hydrogens on our beta, and one is in a wedge and a dash. We can have a cis and trans relationship, so we're gonna have one in a cis and another one in a trans. But we do have to rotate it again, sadly, so that is gonna take a little bit long. Let's see, let me put this one way nicer. So then we have our alpha, and then we have our beta. We have this one on a wedge, a chlorine, then probably we're gonna have a hydrogen on a dash. And I technically just draw what I look in, what I'm seeing right now. Okay. So then remember, we want our leaving group and our hydrogen just on regular bonds. So then this one's my leaving group. So I'm possibly gonna do like a steering wheel method again. And I'm gonna stir that one. But let me see. And I'm also gonna bring these hydrogens down. So I'm technically gonna do steering wheel also. So keeping that in mind, we can do this. Remember, I prefer to keep them just the same. We're just moving the groups. We're not like changing the wedge and dashes. We're not moving those around, just the groups. So then for the left side, I'm just bringing that chlorine up, then my hydrogen, and then this one's going down. Here I'm gonna bring this one up, and then my hydrogen down, and then the other one down. Okay, so then I have a coplanar relationship in here, so I can eliminate this ones. Knowing that, I have a hydrogen on a wedge, and then I have this one on a wedge. Well, I have this one on a dash, and then I have this one on a dash. So then in here I have a trans. So then that one's gonna be technically my major product. And then to save time, or we can always just, you know, we only have to rotate this one. So then let's see, we are gonna keep this one the same just because our leaving group has to be in a regular bond, but we can always change this one. So then we're just gonna move this hydrogen down, let's see, and then this one we're gonna keep it the same. Okay, so then I'm gonna bring this one down, this hydrogen and then have a hydrogen in here. Okay, perfect. So then same thing, double bond. I have my hydrogens pointing up, but I have this one pointing down. And then I ended up with a cis relationship. So then I know this one. Oops, let me make it look nicer. Okay, perfect. So then we can see that our cis is gonna be our minor, while our trans is gonna be our major product. You technically don't have to do all of this. As long as you know that you have two hydrogens, one is in a wedge and one is in a dash on your beta position, then you can technically infer that you're gonna have a cis and trans answers. You just have to remember to flip them. So is there specificity of E2 reactions on substituted cyclohexanes? So we know we have two chair conformations. You have this one, and this is the other one after that ring flip. And one, our leaving group is on an axial, one of the other one is on an equatorial position. The main idea is that when our leaving group is on an axial, we are able to do E2 reactions. So we prefer the one that has an axial position. Warning, our product needs to be on opposite sides. Therefore, the leaving group on the product needs to be on a wedge and dash relationship. So when does E2 happen on cyclohexanes? So we have some requirements. Our leaving group needs to be on an axial cyclohexane, normally represented as wedges, just like that. So then we said we need a wedge and dash relationship. Therefore, our hydrogens needs to be on dashes. So then technically for E2, we're only gonna be able to act with this ones for elimination reactions. Considering that this one is our alpha and this one is our beta, or only beta hydrogens that we're able to act or interact with for E2 reactions are the hydrogens circled with blue. When it can happen, when the leaving group, example the chlorine, the fluorine, or iodine, and proton on beta position do not have a wedge and dash relationship. For example, we do have our chlorine or our leaving group on a dash, not on a wedge, but we don't have our beta hydrogens on dashes. Instead, we have them on wedges. Therefore, they're not able to happen. So for example, we have this our leaving group and this one's in a wedge. Remember, we want a wedge dash relationship. So then technically, if we look at the right side, we're not able to get this product just because that one is in a wedge, but we're able to get this product instead because this one is on a dash. And that also technically explains why we cannot have like cis and trans for that one also, just because we're only able to take one hydrogen, we're not able to take the two of them. So some reminders: when we have side step, the more substituted alkene, and Hofmann, the less substituted alkene. When our base is not bulky or not sterically hindered, then our major product is side step. Some things that are not sterically hindered are like NaOL, NaOH, and remember Na is just an spectator. When our base is bulky, sterically hindered, are really big, then our major product is Hofmann, which is the less substituted. An example of a really bulky base, it will be terbutyl. Okay, Okay, so predict the major and minor products for each of the following E2 reactions. Okay, let's see. So this one is an alpha. Here I have a beta. Then here I have a beta. Here I have hydrogen, hydrogen, hydrogen. So then if you think about it, something that has hydrogen, 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 I wouldn't be able to get priority groups, therefore I wouldn't technically need to do cis and trans. But if I look at my left side beta, then I would have either a cis or trans, not both, just because I have my beta carbon on my left, it only has a hydrogen on a wedge. We don't have two hydrogens on that beta carbon. So then for this problem, we have two options, or we have two products. So then let's do option one. What's nice is that we have a lot of room, at least for this one. So I'm gonna do the hard one first, why not? Okay, so then let's see. Have my alpha and beta. I like to put them like that when I'm doing like stereochemistry, just because I feel like it's more nicer visually to look at what's going on. So then I have a chlorine, I have this hydrogen, I have a regular bond, and then I can just put a CH3, and then this one is just a dash, a wedge, that one's just a hydrogen. And then like I said, this ones I like to just say phenyl just when I do this, just because it will be hard to rotate and just draw that ring over and over. Okay, so I need my leaving group and my hydrogen on just on regular bonds. Taking that into account, like we said, the only thing that we're changing is the groups. We're not changing the position of the wedge and dashes. So I'm just gonna do steering wheel. I'm gonna bring that phenyl up. I'm gonna bring this one up so my hydrogen can go down. And then I want my chlorine up, so I'm gonna bring that chlorine up, that hydrogen down, and that CH3 in here. Once I'm done with that, I can draw my double bond. I have a hydrogen, oops. I have a hydrogen on a wedge. No, that's it. I have a hydrogen on a wedge on this side. And then I have this one like this. I have a phenyl in a dash. And then I have a CH3 on a dash. If I were to draw this, it would look kind of like this. And that will be my answer for that one. So that will be my option 1 answer. So now you can see why it's important to know how to do the steering wheel method. Because now you're able to tell whether it's gonna be cis or trans. But for now, it doesn't really matter until we see what our other product looks like. So then we have option 2, and we said option 2 was way nicer. Okay, so then I have this. So then, since our beta is not really interacting, we're doing this one instead. So then technically we don't really like care what happens with this beta. Oops. Okay, let's see. Let me erase that for a second. Okay, so I want this hydrogen. I'm just gonna put it as phenol, but we already know what's going on. We already know that it's way longer than a phenol. Then I have hydrogen, hydrogen, hydrogen. Then I'm just gonna do my steering wheel method, but I'm gonna do it in reverse. Remember, just keep this one the same. I have my hydrogen, I have my phenol, and then I have my chlorine. Not that way, so then we can do it that other way. I got confused for a second. I forgot that one's my living group side. So now I'm just gonna do it that way. Chlorine, hydrogen, phenol. Okay, so then I have this one in here. I can remove it. And like I said, it doesn't really matter because I'm just gonna end up having hydrogens on both of those sides. But I do have a hydrogen up. And then I do have a phenol down. And we said that it's not phenol, it's actually this whole group. So then if I were to draw it correctly, my final answer will look something like this. I have 1, 2, then I have this, and that will be my answer. And as you can see, this one's mono. This one's mono, while the other one was dry substituted. And if we take into account that this one's not really aesthetically hindered, or it's not bulky, then our major product is gonna be the more substituted. So then that one's my major, and then this one's my minor. Okay, so then let's see. We have an we have an alpha, and then we have a beta and beta. So remember, in here we want our leaving group on a wedge, and then our hydrogen on dashes. So then this one's bulky, so we have to take that into account. Our less substitute is gonna be our major product. So in here we do have a hydrogen in here. And then in here we do have another hydrogen on a dash. So then we have two options. We have option 1, and then we have option 2. Okay, that's it. Oops. I mean, if it wants to write. Let's see, hydrogen CH3. Okay, so then remember, I just normally put tributyl as okay, and then I just take my hydrogen from here. I don't really gonna take this into account for my option 1, just because, you know, they're hydrogens and we're not really interacting with them for now. At least for option 1, we're not interacting with it. So then, therefore, I don't really need to put them when I'm doing the reaction. So then I'll have a CH3 negative, and then my bromine will leave. So then I will erase that one, it will be positive, and then I'm able to do a double bond with that one. So then technically one of my answers will be like this. And I lose that stereochemistry, as you see, because we have a double bond, and it wouldn't be like a chiral center anymore. I wouldn't be able to have you know, a wedge and dash relationship because we have a double bond now. So then on my second option, or maybe I'm just gonna have to draw my option 2 in here. I would actually, since we already did this one, I would actually keep the stereochemistry in here because we're not really gonna interact with that one. We're gonna interact with this one in here. But the thing is that this one is a CH3, so then we do have to show it. Then have my okay. I can take any of them just because we're doing a cyclohexane, so I can take any of it, and I don't really need to do like the whole steering wheel method for this one, because like we said, we're gonna technically lose that stereochemistry anyway, at least for that section, just because we're gonna make eventually a double bond between the alpha and the beta. So then we have in here negative double bond or bromine left, so we have a positive in here, and then we have our CH3 in here. Oops. Okay, so then this one's dry and this one is disopt. So then taking that into account, and then taking that it's bulky, our major product is gonna be the less substituted, meaning that it will be this one. This one will be our major, and then this one will be our minor. So you do have to continue checking on those spaces to see if you got your answer right or wrong. Okay, so then we have the last one. Try it on your own. Okay, so then we have our alpha, and then we have two beta positions. So we have two options. This one's not bulky. Then let's see, hydrogen, hydrogen, hydrogen. This one stays the same. We have our OH in here. We have our negative. Let's see, alpha, beta. We still technically cannot do anything. Oops. Because I technically want to rotate that one. So then let's see. We can do this. We have my hydrogen, hydrogen, hydrogen. Have this one on a wedge, this one on a dash. So this one's just a regular bond. And remember, I want my regular group and then my leaving group and my hydrogen to be on regular bonds. So then I'm just gonna do steering wheel for this side. Just gonna keep regular bonds in here. I'll bring my hydrogen up here. We'll move, let's see. I'll move this weird thing here. And then, let's see. I'll put my bromine down here. So then I can put this one down, and then I can just do this. Hydrogen, hydrogen. And then I will have a wedge hydrogen, and then I will have a dash. 1, 2, 3. 1, 2. 1, 2, 3. Okay, perfect. Let's see how this would look like without the hydrogens. Okay, I was worried for a second that we didn't get that one right. Okay. So then that one's one of our answers. And then we have option 2. And for that one, we're also gonna have to rotate. So then we have our hydrogen in there. So then we have our alpha and beta. We have an alpha bromine, a hydrogen on a dash, and then just a regular bond CH3. While in here we have 1, 2. Have a hydrogen on a wedge, and then this CH3 on a dash. So I want my leaving group and my regular hydrogen, or my regular, and my hydrogen on a regular bond. So then leaving group, I'm just gonna draw everything just the same. I'm just gonna move my molecules. Okay, so then for the left side, I want my bromine on a regular bond. So then I'm gonna move my hydrogen up, my CH3 up. I'm gonna bring my bromine down, just doing some steering wheel. Then for my right side, I'm gonna do it in reverse. I want that hydrogen up, I want that CH3 down, I want this weird thing down. So then I'm gonna have my bromine and my hydrogen up like this. So then I can have a double bond. So then what's pointing up is my hydrogen, and then my CH3. What's pointing down is my CH3, and then this one's down here. So then if I were just to draw it without my hydrogens and the CH3s, it would look technically just like this. Then this one's dry. Oops. This one's dry. And this one will be a mono. I have a mono and a tri, making the mono one. Since this one's not bulky, that means that the mono one is gonna be the minor product, while the major product is gonna be the tri-substituted. Okay, perfect. And then we can make a stop now, and then we can do SN1 and E1 for the next time. Hopefully this was a little bit more helpful with dealing with E2 reactions, and I hope you have a wonderful night.